I will apologize in advance. I'll be very cursory in this, but we can always ask more questions in between. But since spatial frequency domain imaging is the core of what my group does, I'm going to be talking about that because I think it's the most important thing. It's what I do. But is that all right? Oh, sorry. Yeah, no, it's.
I can edit it later, but I'd rather not.
Yeah, yeah. No, I could understand.
I think it's just this one. Let's see. I think we're good now. Let me check.
Okay.
I think I just.
So, okay, good. So yeah, so for today, again, just some of the teaching objectives. We're going to kind of bounce around, so keep it very informal. Interrupt me as we go. I think that's probably going to be the most beneficial way of doing this. But again, since we'll be followed up by Carol and talking about inverse solver strategy, I just wanted to kind of take a step back, look a little bit more broadly on the kind of fundamental motivations behind diffuse optical techniques in general. I'm going to be touching on the spatially resolved and spatial frequency. Tomorrow, Tom will be talking about other diffuse optical techniques, but to kind of say, what's the whole point and why do we kind of coalesce to these different approaches of visioning how light transport happens and how do we get stuff out of it. Then go through some spatially resolved methods, strengths and weaknesses there to provide some context. And then with spatial frequency domain, going into a little bit more of the practical and pragmatic aspects of how do you actually acquire the data? What do you need to be thinking about in design considerations? But then also kind of saying, what do you do with it? Where is it useful? How can you configure a system for specific things? And so that's this concept of SFDI. Of course, this is thanks to Bruce to have SFDI over space, time, and energy. But, it's basically saying you can configure the system in a lot of different ways. So if you want to have something that's fast or cover a lot of area or get a lot of detail, what do you do and where is it useful? And then time permitting, talk about some hybrid methods where you can combine SFDI with other techniques or other directions that are still in development and still being explored with spatial frequency domain imaging. So, that's kind of the agenda. We'll see how far we get. But, to kind of go through and start at a very high level, again, I typically will like to have this very cartoon version whenever I speak, just to present to people in a very simple way, just where my mindset is and how I kind of approach things, because everyone looks at it a little bit differently. So when I talk, no one really understands me. So this is where I start. So this is kind of how I picture light interaction with tissue. So, you have the little cartoon here where you have light coming in. There are different objects that will redirect the photon and kind of rattle it around. And that's the cartoon version of scattering. And with scattering, why is it important? You can actually have sensitivity to the kind of mean density and mean size distribution of scattering objects within tissue. So, and these are the subcellular and extracellular components. So there is a relation to the physiology in that data. So why is scattering important? There's a mechanistic aspect. It's what distributes light throughout the tissue, so it can interact with different things. But you have also this relationship to actual kind of structural components in a very loose term with what's going on in tissue. You have absorbers in tissue, so light comes in and it terminates the propagation of the photon, the energy is transferred, and that's usually with a molecular sensitivity to things like hemoglobin, melanin, lipids, water, carotenoids. You could have a lot of endogenous and a lot of exogenous things inside of that. And again, you can also have fluorescence. And again, fluorescence being a little bit more of a complex process. There's an absorption phase and a re-emission phase. But again, these are the primary things. And these are usually the things that I think about when I look at light tissue interactions. There are other things. There are more complicated things, but usually this is my parameter space because Otherwise, I get too distracted if I have too many things in my head at a given time. So, but for fluorescence, endogenous, you have collagen and elastin, NADH, FAD are the classical things that people will refer to. You could have other exogenous fluorophores present, but when I usually talk about light interaction of tissue, that's the extent that I go to. And of course, I don't think anyone needs any reminding here. The idea of this kind of molecular sensitivity from absorption and fluorescence, structural sensitivity from scattering, that there are a whole variety of tissue conditions, diseases, and states that can be extracted by combination of all of these. And so that's always what makes it really appealing is, for any type of classical disease, you have multiple signals from the absorption side, multiple signals from the scattering side, all can kind of contribute towards informing how that works. So, you have these kind of, what people have been referring to as optical biomarkers for these different things. And it's always the combination. The hard part is, well, how do you isolate everything? How do you measure everything precisely? But there's information there. It's just our job now to figure out how best to extract it. So, the classical challenge is, if that's all the stuff that's happening inside of tissue, what we actually see is a black box. So, we only detect what light comes back out relative to what we send in. So we're not really sure where it went. We're not really sure what happened to it along the way. So, we need to kind of think about now, all right, how do we do this? And this is getting into this whole inverse solver type of approach. If we know what's inside the tissue, we can model that. That's already done. That's a problem that, in the practical world, we don't need. We need the inverse of that. So again, going through what you've already been introduced to, we have that forward problem. If we know what the tissue is, what our real need is the inverse to say, what kind of measurements can we make to inform the model well enough so we can back out what are the parameters that actually generate these results? And again, this is something where an inverse problem is usually ill-conditioned and ill-posed. You have to think about all the different things. So what's the classical approach to overcome this in our field? Well, the first question is can we reduce the parameter space? What are the variables we're really interested in? What other variables can we just assume or say is constant to reduce the dimensionality of that? So that's where typically things like index are assumed. Anisotropy is assumed, and especially if you're looking at large areas where it's diffuse, it has little impact. So there are different things where you can kind of minimize these variations in those parameters. But then, that's usually not enough. So if we're measuring reflectance, how many different ways can we measure? How many different unique measurements can we get? The more measurements, the more way we can kind of combat this ill-posedness. And, again, we look at our radiative transport equation, and we can say, well, how do we manipulate this? By making different measurements. So again, from the equation standpoint, we have our source term. We can manipulate the light source that we use as a form of a perturbation of this equation and try to go through and now get multiple equations to try to tease out and differentiate what's absorption and scattering. So again, here in this case, like with spatial frequency domain, rather than just shining light, we shine patterns of light. So there's an encoding aspect to the source. And then we can also look at spectral responses and say, well, we know what kind of chromophores we expect. If we use different wavelengths, we should get different outputs relative to the absorbers and scatterers present. But we can also look on the detection side and say, well, there's an angular component in the very subdiffusive part. There is multiple distances that we can look at, so we can make measurements multiple distances away. And now you have multiple measurements over different conditions of the same tissue itself. You can start to use this to feed in an inverse solver to really narrow down what are the unique optical properties you have present in the tissue. So hopefully, so far, this has been light. This is something that you already know and you're feeling comfortable with. You're comfortable with it? Hopefully. So yeah, so with the detectors, the question is about, just to explain how you can get the different measurements at the different detectors. And so, in this case, typically it's at different spatial locations. So, again, if we make a measurement, we're shining a source in, oh, of course, I point at the wrong thing here. You shine light in here. If you look at what comes out at different locations here, they're probing different parts of the tissue. It's a different perturbation of the radiative transport. And so that it should be the same absorption and scattering. The different results should be from the different positions you're looking at. That's where you can do this inverse solver. So canonically, this is something that, I think David already showed, and it probably was shown in previous slides, that, there are these 4 different domains of making different reflectance measurements. So we can do it spatially, where you shine at a given point and then see what the response is as a function of distance from that source. And you get this kind of response curve. The shape of the curve is derived based on contributions of absorption and scattering. You can also do it in time and shine it pulse in, and then look at the temporal response curve of that. And then, of course, there are the Fourier transforms of that. So with a spatially resolved reflectance, a point source, the Fourier transform is a sine wave. So you have the different spatial frequencies with a delta function in time with a short pulse. The transform is an oscillating beam at higher spatial frequencies. So we have these different components. And again, I'm not going to go into too much detail here because I'm sure this will be explored in much greater detail tomorrow. But, these are the 4 different things. And again, I had mentioned to some people the other day, when it comes to doing research and as a PhD student starting out, you're focusing on one technique, trying to solve one problem. It's always useful to have the context of what else is out there. So what can your technique do that's better than others? You have to really know what others can contribute and leverage that back and forth. So, with these different techniques, the way they have the different measurements of reflectance essentially is by having these measurements experience different path lengths in tissue is one way to think about it. It's this thing that Bruce Stronger used to refer to as differential reflectance. And so, in the time domain, you can think of it as time of flight, of the photon within the tissue, is related to the distance it travels. So one photon or collection of photons travel a certain distance, experience something, someone goes a little bit further, may experience slightly more of one thing or the other, and that's how you be able to kind of parse out the differences. In the spatial domain, the distance from source detector constrains that it has to travel a longer distance. And so that's this kind of differential path length. And, in general context, we can kind of look at these different domains and see what are the advantages and disadvantages. And this is very high level, very generalized. So I'm sure, people may take offense of, the oversimplification, but, we have, time domain techniques. And, again, the advantages really are the depth and the volume, but at the consequence of the resolution and having to have a very short pulse, equipment tends to be quite expensive. You have to have a very fast source. You have to have a very fast detector. Frequency domain kind of takes advantages of, oscillating sources. So there's a little bit of relaxation on costs, but pretty much the same thing. Spatial domain, also point source, and probe based, not as good as deep, or not as deep as the other techniques, but there's clear cost savings. There's a practical aspect in implementation. And then finally, spatial frequency, where you have something where now it's an imaging paradigm, but having it being a planar illumination imaging paradigm, you're very limited on depth, but you have now a lot of spatial information. And the costs can vary based on what you want to do, how sensitive your instrument is. So that's kind of the general landscape of what's going on. So now from there, if we can take a little bit of pause if there was any questions. Again, this is throwing just a lot of things out at you and in a very general, non-specific way. So So with the spatial domain and spatial frequency, so spatial domain, it's usually a probe-based system. So you shine light in a certain point, and then you have multiple fibers a distance away to detect what's coming back. Yeah. And spatial frequency, it's basically you have an imaging system where you shine a pattern, and so it's how the patterns of light, and we'll go into it a little bit more. It's a little bit tricky to try to visualize what's going on there. But yeah, so those are the main two differences between the two. We'll go into that, but in general, the characteristics are things like breast, brain, deeper organs, the time, frequency, and spatial domains are the ones being used because of the geometric advantage of having that fiber setup where you can constrain the depth of what you probe. Spatial frequency, you are constrained to just shining light as a image, and so you can't do any separation in distance. You're always looking at a single pixel and a single point going in and out. You tend to be much more superficial, but nice thing for us is, the hundreds of microns to millimeters, that's the domain of skin. So there's a lot of stuff we can look into those types of things. Yes. Oh, yeah, that's, again, it can be somewhat controversial. So, there are different configurations that can be slightly higher resolution and all that. So, yeah. So, when I talk about, probe-based systems having a centimeter resolution, they're like, well, we can actually get millimeters. Yes, it's true. So, but yeah, so this is, a very generalized thing. So, talking about spatially resolved methods, again, some of these graphics should be familiar to some people in the room since I just stole it from them. But just to kind of give the layout and visualize what's going on, we talk about a kind of pencil beam and then multiple detectors at different distances. And the kind of motivation for this is that for each distance farther and farther away, you are getting slightly larger depths, slightly longer distances. You get this kind of differential reflectance information that is necessary to do the inverse solver for your light transport model. And again, as shown before, from diffusion, you can get very simple relationships with this. It's really easy to work with when you simplify it to a diffusion approximation. But you've also run some simulations already in Monte Carlo, and you can see that, as a function of distance, the signal that you get is very dynamic. It drops off really fast. And so there's this huge dynamic range of information in there. And that, in very short distances in the non-diffuse region, you have, more scattering events than absorption. The farther out to go, the greater the volume of tissue it probes, it's going to be encountering more absorption. So you have this kind of, as a function of different contributions of absorption and scattering. And that's really where the inverse solver can come out and isolate those two. So, this has been used in a quantitative spectroscopy setup and in different cases here. So this is, a very old system, but, this is where I was first introduced to it, was this system that came out of Tom Foster's lab at the University of Rochester, where you have a probe where you have a central light source and this kind of spiral of detectors around, where you would have multiple distances relative from the source to the different fibers. And then they took these fibers and put it up into a coherent array so they could send each fiber into a spectrograph where each linear array of the spectrometer correlated to a specific fiber, so a specific distance. So you can get multiple distances and high spectral resolution for all these cases. And so with the multiple distances, then they can separate absorption from scattering. And then this was an example, here, of different concentrations of hemoglobin in a liquid phantom, where they could have the simulated results and what their measured results with their inverse solver would provide. So again, quantitative results, high spectral resolution for cases in homogeneous media. So, in a more practical sense is cerebral hemodynamics. So, of course, I refer to what I know best, which is really just my own work. So I apologize in advance. But, this is what we were doing and looking at multi-distance configurations. And again, really exploiting this idea of different fiber separations, look at different volumes. When you look at cerebral hemodynamics in a probe-based system, you're always going through the scalp, the skull in order to reach the brain. And there are hemodynamics in the scalp that are always going to be present in your signals. So how do you isolate the signals that are unique to the brain from everywhere else? This was this concept that we had where we could have the short source detector separation, sample superficial fluctuations in hemodynamics, where the farther ones will have both the superficial and deep signals encoded in that. And so, again, very homebrewed system. I mean, somebody had asked me a couple months ago about this thesis work, and I was just thinking about it and all the equipment that we had to build up this system. I'm like, I think you can do it on your phone now. So it's kind of embarrassing, but yeah, it was a very homebrewed system that we were testing out, built from scratch. And yeah, we just kind of made the assumptions, of index and anisotropy. We assume that the only fluctuation in the signal would be due to hemodynamics, that scattering is present, scattering is unknown, but at least scattering doesn't change. And we made general assumptions on path length, but the important part of our technique is we recognize that everyone's skull, everyone's scalp, the size of everyone's head is different. Different locations are also going to have different thicknesses. So what we were developing was an adaptive method to really relate the two signals and scale them automatically for any geometric variation in that patient itself. And so that's where we actually used the temporal fluctuations as a kind of lock-in signal of the superficial versus the deep, and used that to adjust for all the geometric parameters. And what that was able to show is that under standard NIRS, under very good conditions, so, again, this was a visual stimulation protocol. This was about 6 stimuli. So in standard NIRS, that's actually pretty good to get, a correlated signal with activation with only 6 stimulus periods. So, by NIRS standards, that was really good. But, what we were really interested in is, can we actually look at and identify individual responses? And so if we try to model the individual response, we got, a lot of model failures, a lot of things where it didn't correlate with the noise. But with our corrected method, where we could decouple any global or superficial signal and just isolate the thing that was mathematically unique into the brain, we got better separation here, which looks nice. But the more interesting part is we can now model all the individual signals and clean that up. And so you can actually look at individual signal responses. Yes?
Explain that again. So for the NIRS, you try to look.
Yeah. Yeah. So with the NIRS, we just used the far source detector separation. So we just adopted the general technique everyone does, did the standard, changes in oxy and deoxy with an assumed path length factor, and just process it that way. And then the corrected NIRS is where we did the scaled subtraction of the signals we detected here to try to clean up the signal. The question was, are the hemodynamics underneath this sensor the same as over here? So are you making things better or potentially adding more noise because it's differential? And so we spent a lot of time to prove that primarily, a bulk of the signal really was this kind of global thing, that superficial changes here were the same as superficial changes here, and that it would actually have a net benefit. So Mhm.
Did you try
Yeah, my supervisor wanted me to graduate.
yeah, well,
No, I mean, literally, that was, once we finally got this up and we were proving that it was working, we were like, oh, yeah, we could do all these extra things. But yeah, we needed to move on. But I mean, yeah, there's a lot of open-ended questions, a lot of things that we didn't get to just from this first part, because it was just to be able to kind of prove and justify that this added value was a hard thing, because there was no phantom model to prove this. No one really knew the physiologic dynamics in vivo, so we had to do it all in vivo and try to set up experiments where how do you go through and prove something's working if you don't know what the answer should be? And so there were a lot of these thought experiments that we would work through to try to resolve that. And so, we were, happy and quite pleased with this, because I mean, even with this, you can look at the residuals and you can almost see, there's a little bit of a dip here. There might be some additional effect going on. But rather than just relying to say you have to have tens, if not hundreds of it, and just look at the average response to compensate for all these other random fluctuations, we're getting something where we can actually get individual responses and look at that. And so you can start to look more closely, look at differences between responses at one point in time versus another. It can start to ask a lot more questions. But yeah.
So what
So, I mean, it was just the very simple, um, yeah, now you're making me think almost 20 years ago. Um, yeah, but I mean, it was the standard, we had two different wavelengths, fluctuations of signal, assumed constant scattering, assumed a given path length and a differential path length factor for each wavelength. All the stuff basically what Boa's group was doing and everyone else was doing at the time, and just calculating delta, oxy, and deoxy. So, there was nothing really fanciful in what we were doing, not very different. The main question that we had was, we had now these hemodynamic signals at two different source detector separation. How do you scale one appropriately to the other? Because that required, to do the rigorous solution, knowing the geometry, knowing the optical properties and path lengths more precisely for every layer. And what we said was, well, if the signals are, from multiple sources, you could, you collect a long enough time frame, the unique signals will become more and more orthogonal from each other. And so least squares should be able to determine what that scale, what component, what kind of weighted coefficient of one signal is in another measurement. And that's really what we had. And that's where we went from. So
maybe doing it today?
Mhm. I mean, I think if I were doing it today, I would really, I mean, given the trauma that I went through to build up this system, back in the day, for me, I would say, looking at simple instrumentation. I mean, I think collecting more data, and really just saying without any expectation, just get more and more data over more subjects to really just make sure, because that was, at least at the point in time of this thesis, the biggest issue that I perceived in the field was everyone said, oh, we present a simulation, there should be this response. Everyone, it became kind of this, confirmation bias that, if you can get, if you get the thing you were looking for, it worked. If you didn't get it, there's something wrong with the technique. And, what we were doing with a lot of the thought experiments, by setting up experiments where we had no expectation, we could actually learn a lot more. And, our realization was, yeah, people were looking for signals and it wasn't the signal that was actually present. So they ignore, they would miss other things. So I think that was the whole big thing is, you don't want to be too confident to say, oh, functional activation, you're going to get this type of increase in oxy and, maybe some decrease in deoxy, and that's the signal you're looking, having that kind of preconceived notion really limits, and, it may not be true. So it's a plausible thing. Always be careful for that. That was just my experience. I mean, yeah, I had to go through a period where there were a lot of people are just saying, "Oh, this doesn't work. It's all bullshit," and stop wasting your time. At one Gordon conference, there was a person who basically told me that I should just give up and find other work to do. The world needs mechanics, and yeah, I mean, at least for me, that actually made me much more motivated to really make this work. But it's still, in hindsight, not very pleasant. But yeah, so this is just one example. There's a lot of other stuff. I haven't really been too engaged in this field since then. So I'm sure there's a lot of other things going on, but this is just more anecdotal perspective from an old man, I guess. So yeah, so again, like the large take-home messages, and the things that I had experienced, especially with instrument design, is even though it's simple and low cost, trying to do multi-depth sampling and multi-distance measurements with this, what I always encountered was the fact that there was such a large differentiation in dynamic range that you had to play a lot of games to really balance signals, maintain signal to noise in these types of setups. And so, yeah, I mean, going back to this, we had the original idea that we had these large fiber bundles in the far source detector, a small fiber for the short, so we could try to balance the signals. It was a nice idea. It was still off by several orders of magnitude. So, I mean, it's a little bit of a challenge, but, to kind of think about that. But, there's a lot of things that you can play around with, get some sense of. So that was all that I had for, spatially resolved. If there are any other questions on that before we start going to spatial frequency domain. Yeah. Yeah, so this was CW. Yeah, we kept it as simple as possible. Yeah, I mean, the other anecdote of the system that I had built, the secretaries in our department would no longer talk to me because I needed a way to have nice pressure of the fibers against the skin. So I would steal all the springs from their pens and then return the pens without springs. And so, yeah, yeah. It was good because you could really think of what the problem was and come up with creative solutions. But yeah, the administrative staff was not as appreciative of my creativity in that regard. So, but yeah, so then we'll go to spatial frequency domain imaging. So again, the concept is out there and stuff. So I just wanted to start at a very high level as to kind of what this technique is and how it actually works, what the principles of operation are. And so in terms of instrumentation, again, you already heard David's talk, so there'll be some things you might have seen before come up here again. But, it's very appealing for the fact that in theory, all you need to do this is you just need a projector and a camera, and you can do spatial frequency domain imaging. So that kind of low barrier of entry is really nice to kind of explore things. But then the question is, well, what do you want to use it for? Adds to the complexity, adds to the design specifications, and it can build up and escalate quite quickly from there. But as a concept, that is what this technique really kind of comes from. And, from David's paper, the nice part is that with this kind of concept of shining different patterns of light based on the frequency of the pattern, you can see a differential response if you have constant scattering but change the absorption. You have a family of curves here that, as the different frequencies, you have different shapes in this really nice, smooth, monotonic decaying curve. The benefit of this versus, the previous technique of spatially resolved is that the signals here don't go down orders of magnitude when you change the spatial frequency. So, the dynamic range is much shorter, so it's much more convenient as a sensor to work with this. But, with this is how absorption changes you have a unique set of curves. When scattering changes, you have a different response. And so again, this differential response is how we can kind of separate the two. And, one of the challenges that I had my PhD students when they first come in, it's their first introduction to SFDI. I try to ask them to try to conceptualize how the technique works in their own way. And so, when it comes to this, sensitivity of absorption at low spatial frequencies and, what does absorption do to the spatial frequency domain imaging? One of my PhD students says, well, you start with a pattern like this, and if you increase the absorption, basically what you do is attenuate the signal. The pattern stays the same, it just gets darker. Yeah. The period of the pattern. So, I mean, yeah, you can try to do different patterns in different space, but then that's going to be a different spatial location. So there are a lot of multiplex techniques, and we'll get into it if I don't talk too much. But yeah, so the idea, and we'll kind of go into a little bit more what this sequence looks like, because we'll go into the data flow where, what do the different spatial frequencies we typically use look like and all that. So we use the usually typically 5 to 11 different spatial frequencies, from a planar illumination up to a sinusoidal pattern of 0.5 per millimeter, 0.5 cycles per millimeter. So that's usually the range we can work with. You can definitely go higher. You can definitely have different types of patterns and stuff. And so, yeah, we'll go into that. Yeah. So absorption, basically the net effect is it attenuates the signal. Yes. We make it up. I mean, it is a very open discussion. There's actually been a number of papers on how many or which combination of spatial frequencies are best. I think, it really depends on the application. What are you looking for? But yeah, I mean, it's a complicated thing because, different spatial frequencies are going to be looking at different parts of the tissue. So, you can get better separation of absorption and scattering with a low spatial frequency and a really high spatial frequency, but they're also going to be probing the most disparate parts of tissue themselves. So it's sometimes better to have things closer. So it's an open-ended question. And yeah, I mean, people have looked at that. There's no clear answer. So yeah. So we have, digital projectors. Yeah, so like a digital micro mirror device. You can have other ways of projecting, and yeah, we'll talk about some of them, like static masks and different things. So yeah, we'll get to that. Yeah. Yeah. Mm. Mhm. Yeah. So, I mean, there are, this whole other field of photoacoustics where you would use light, pulse it. So you would basically have energy transfer in such a short period of time that it actually creates a thermal response that creates an acoustic wave back. Yeah, I've been talking to a lot of them on a lot of problems they've been encountering. And so they will have, discrete points. There's talk about having a spatial frequency type of illumination pattern and trying to deal with that. But yeah, so I mean that goes in a different thing, and that as the multimodal approach. So I mean, we can talk about that later. But again, that is a further extension of this. So yeah, maybe we'll just stay at SFDI at a conceptual level and not go to any more slides. But yeah, so we have basically the darkening. That's what the effect of absorption is. Absorption doesn't change trajectory of the photons; it just reduces it. So, the pattern itself remains intact. The relative contrast of the sinusoidal, pattern remains intact. It just gets attenuated overall. And then if we look at scattering, and of course, the interesting aspect here is that at the higher spatial frequencies, we really lose contrast and absorption, but contrast and scattering persists. And the way to kind of think about how does mechanistically scattering impact these patterns versus absorption is here. If you have a pattern, particularly at a higher spatial frequency, it doesn't make the pattern overall darker like absorption does. What scattering does is essentially blur out the pattern. And so you lose the contrast. So you have these two different mechanisms. One's making it darker, one's making it lose contrast. And so those are the two things, and the advantages of having encoded patterns of light is the fact that you can look at essentially fringe visibility and overall signal. And those two are loosely correlated between what's being scattered and what's being absorbed in tissue. So, and we talked before about differential reflectance, when we were talking about time domain, temporal frequency, spatial domain, it was all about the distance the photon traveled. And the way that it would work with multiple measurements is that each one travels a different distance. When we're talking about spatial frequency, it's kind of hard to imagine, you aren't going from photons at one point to another. You're looking at this ensemble average of patterns. And so the way you could think about the differential reflectance in spatial frequency domain is that if tissue is a low pass filter, as the pattern propagates through the tissue, the scattering will kind of blur it out, the absorption will attenuate the signal. That's kind of what we were described as fluence before. Here, it's about the fluence of the pattern integrity, not just the total optical signal. And so, again, low spatial frequency, scattering is just going to deviate photons a small amount. So it has to go further and further before it blurs that out. But if you have a really fine pattern, it's going to blur up much quicker. And so, just looking from the fluence, we can see that at low spatial frequencies, you can have that pattern propagate much deeper into tissue, but at higher spatial frequencies, it drops off really fast. So effectively, you're looking at different penetration depths in this paradigm, and that's the differential reflectance part for spatial frequency domain. So how do we actually acquire data? How does this technique work? What are the different tricks that we have to kind of go in order to get this, amplitude response, this spatial frequency dependent reflectance signal? So typically in these systems, we have a sequence of multiple patterns. So, again, we start with plane illumination. That's a spatial frequency of 0. And then, slightly higher and higher spatial frequencies. So it's usually a sequence. And at each of these spatial frequencies, we actually collect we shift it 3 different phases. And so that might seem a little bit weird and complicated. You're like, all right, if you're shining different patterns, why do you need different phases for that? And, the motivation for doing that is if you want to get what the amplitude of a sinusoid is at any given location, with a single frequency, you have to model that curve in order to determine where that is, because you don't know if you're at a peak or a trough. And so you would lose spatial information because you have to look at your neighboring pixels to really determine where in the sinusoid you are, and then what that amplitude must be. When you do 3 separate phases, again, you have this overlap, and mathematically, it becomes arbitrary. So long as they're evenly spaced between each other, you can calculate what the envelope function is. And that essentially is the amplitude of that AC component. So, we use that. It gives, a nice even signal to noise across all the sample and extracts our AC component, and that's our spatial frequency dependent reflectance. And, if we go through multiple patterns, 3 different phases each, we can then get what the amplitude is at every given pixel. We now have these reflectance measurements as a function of spatial frequency. And even in these examples, so this is the classic example at low spatial frequency, in the near infrared, you can see veins, you can see that absorption contrast, but we already know that as you go higher and higher in spatial frequency, your sensitivity to absorption drops off quite quickly. And if we look here, you can, if it renders it correctly, as you get higher, you lose that absorption contrast. You don't see the veins anymore. And that's where it's shifting from something that's highly sensitive to absorption to something where it's more sensitive to scattering instead. So that's the kind of transition. So, yes. Mm-hmm. Yep. Yeah. 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 No. I mean, it's good that we're on the same wavelength here. So yeah. No, I mean, when we do this demodulation, and again, as it is a complicated process in data flow, there's a lot of things as sanity checks as you go along. And so, yeah, I mean, from the demodulation itself, we've been actually using it as a diagnostic factor for these different questions. So, again, one of the most common things, especially if you're trying to do a low-cost system, you're buying a commercial projector. Commercial projectors are designed for visual aesthetics. So they will project patterns in a very non-linear way. So there is this gamma correction that they have that's supposed to be better for the visual response of the human eye. So when you go through and input an image of a pure sinusoid, when it's projected, it's actually distorted because of this nonlinear response. And so you always have to correct for that. But yeah, so, you would, I mean, we just pre-distort for the low-cost system. Since we can't get direct access to the DMD itself, we pre-distort our images. So when they are then projected, it compensates for its distortion. So you get a linear pattern. And the way that we verify it is, so, we run through basically planar illumination patterns of the projector at different bit intensity levels, and then kind of map that out to say, this is what we're telling it to project. So something that is 10%, what do we get? 20, so on and so forth. And that maps out also the nonlinearity of our camera. And then the final result is we can do the 3-phase. If we don't see, well, we try to just do it for the projector itself. So if we are having LEDs, so if it's a LED projector, it should be the same response for the DMD. So it's more the DMD response. But yeah, we verified at all wavelengths. So yeah. But yeah. So far, it's been a single correction, and it's not wavelength dependent. So at least with the, I'll be cautious and say, we haven't had that problem. Doesn't mean that the problem won't exist somewhere else, but yeah. But I mean, the nice thing is you can easily verify it, and look at any residual frequency patterns, and based on the period of the pattern versus the period of your frequency, you can see if it's this nonlinearity. It's usually a factor of 3 higher. factor of 2 if you have fluctuations in your light source. So, you're doing usually 3 phases sequentially. So if you have an LED that is flickering, that you would have, say, 2 that are of the correct intensity, 1 that's slightly lower, you will then get residual modulations, but it's at a different frequency. So you can actually diagnose the problem based on the period of the residual. So yeah, sorry. Mm-hmm. Mm-hmm. Short answer, yes. I haven't really thought too much about it, but again, you have this, it's a volumetric approach. You have the ability to look at different spatial frequency responses, which would be different depths. So yeah, if you had something that is just a flat image versus something that is, differential, something that is turbid and has volume. Yeah, I mean, by principle, this should be able to tell the difference. So yeah, so we have this, you have this 3-phase demodulation, and it's nice to be able to kind of diagnose things. The very first case, this was actually a very common issue that we had at the early stages of spatial frequency domain imaging. And again, I blame Bruce for this. So it was very new. Bruce would always bring people in to showcase while we were making measurements. And so, nice sequence of flashing lights and flashing patterns. Everyone would look over, cast a shadow, and for every single phase, all of a sudden you would have changes in the background illumination, and that would screw up this 3-phase demodulation. So it was just like, I would do stuff like try to put tape around so people could see, but only from a distance. And if Bruce, that doesn't work. He's going to go in and point at things anyways. So, but yeah, so I mean, that was kind of like the background motivation to say we could actually kind of diagnose things, because from here, when you're acquiring data, it's always good to have some sense on whether the data is going to be good enough, because the processing can take quite some time. So any indication early on is kind of important. So from here, you have calibration. So we have turbid phantoms that we use. So phantoms with known absorption and scattering to characterize the system. And that's because any raw measurement we make, well, it's going to have the reflectance of the sample, but it's also going to be influenced by the sensitivity, the performance of the system. And again, that's this instrument function. And the instrument function can be about the optical characteristics, the light throughput, the light source you're looking at, the sensitivity of your detector, and all these different factors all bundled together. But the idea is that if you have a phantom with known optical properties, you know what its response should be at every single wavelength of your system, that you can go through and run a forward Monte Carlo model to say, okay, if I know the answer of this one thing, I don't know, this black box of tissue, but I know this one thing, and these are the optical properties. When we make a measurement, our reflectance values are scaled and varied due to our instrument function. We can use that because we can run the forward model and compare to what is actually measured. And so that's where we have this calibration scheme where we take a measurement of our sample, of our tissue of interest. We take a measurement of a known phantom. We divide the two. And just by dividing the two, you have the same instrument function. It's assumed, especially if you do it back to back, that the instrument hasn't changed. So taking the ratio of these two will cancel out the instrument function, leaving you with a ratio of your sample to your phantom. But if you know what the phantom optical properties are, you can run the forward model. So a Monte Carlo of those different things, and you multiply it by that, that cancels the other two out. And now you're just left with the reflectance exclusively from your sample. So with all that, you now can kind of have a calibrated system. And yeah, to Vassen's earlier question, when we calibrate, We do it at every single wavelength. We do it at every single spatial frequency, and we do it at every single pixel location because, different wavelengths will have different intensities, different sensitivities of the camera. Different spatial frequencies may have greater sensitivities to optical aberrations in your system that you want to have characterized. So it's important to do it at the different spatial frequencies. And, even as the illumination distribution as we would want to get in an ideal case, every pixel location might have a slightly different intensity of the light source. So there might be some distribution that you want to compensate for. So that's why we do it at all these different cases. And then we get our calibrated reflectance and calibrated reflectance curves as a function of spatial frequency. So now that we have this calibrated, and again, the next sanity check is when we're looking at these, and again, this is just looking at a single pixel, essentially. You can look at the image. The calibrated reflectance, you can ask the question of, is it between 1 and 0? If you have negative reflectance values, that's non-physical. There's something wrong with the calibration system. Is it greater than 1? Well, that's obviously also something wrong. If it's between 0 and 1, there still could be something wrong, but at least, you are eliminating the obvious case. The other thing is when you're looking at, the higher and higher spatial frequencies, scattering is blurring out the amplitude a lot. The residual amplitude could be as little as 5% of the original signal. So if you have high noise in your system, you're going to have really noisy signals. So you can also look at the higher spatial frequency and say, does this just look noisy to me? Because if we're going to try to put it into a fitting algorithm, an inverse solver, there's no point if it's noisy. So you can identify any issues early on from this. So there is diagnostic value in that, because once you go to the final stage of fitting, this is your inverse solver. This is where it's going to iterate. And if you are comparing, simulated results, your forward model to measurement, if the measurement data is noisy, it's going to go off the rails quite easily. So, this is the time-consuming part. And this is, where you wanted to have as many sanity checks above that. So again, Carol's going to tell you about inverse solvers and that process. For spatial frequency domain imaging, there are different models, different solutions for the radiative transport equation that have been utilized in spatial frequency domain imaging. So again, there's the standard diffusion approach. I am trying to avoid using too many equations, so I will refer to the paper. You could see the derivation of that and also just utilize the result from this. But again, standard diffusion, near infrared, low spatial frequencies, where it's more diffusive, the higher the spatial frequency, you're going to violate the conditions of the standard diffusion approximation. But that's at least the starting point for an analytic approach. And the nice thing is for an inverse solver, if you have an analytic equation, you still have the iterations, but at least it's very fast to calculate. Of course, if you want to get better, again, there's the delta P1. That's what we have adopted in my group now as an analytic solver. And, I was trying to see, is it posted online? Insux thesis. I think it might have been yeah, yeah, this I just got from one of Luigi's references, but yeah, it is in the appendix, and that's what we've been using. Okay. Yeah. Okay. 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 Yeah. So there was a nice derivation there, and I think there was also just the standard diffusion derivation as well in those cases. So, I think it was very useful for my PhD student because it had the full derivation going through, so you can kind of learn all those different steps. But those are the different references for analytic solutions. But of course, Monte Carlo is the best. So, how do we do a Monte Carlo solution for spatial frequency domain? Or before we get to that,
Okay. Like what domain?
Mm.
Hybrids.
mhm,
You just look at how much amplitude light signal you're getting.
yeah. Yeah, no, I used to have a slide, just an example of, calibrated reflectance, and it was this matrix as the different wavelengths and the different spatial frequencies, and you can kind of just visualize what the noise was. So, there's really no clear guidance. Usually what we'll do it is based on, we know we're looking at tissue, and the more granular, the more variation you started to see at the higher spatial frequency. Again, you can assume that's going to be noise versus actual tissue property. So, there isn't any clear guidance. And again, when you're doing the fitting, you can weight it that there's less weight to the higher spatial frequency because it's going to be more noisy. But there are a couple different ways. But to my knowledge, there's no clear, this is the best way to do it. People just kind of more empirically say, I feel comfortable with this, or I feel more confident with that. But there's really no clear approach to that. Yeah. So, how do we use Monte Carlo solutions as an inverse solver? So I don't know, Carol, are you going to be talking about that at all, or just the minimization? Like Monte Carlo. Okay. So at least there is the introduction, so I don't need to go into too much detail on this. So yeah, I mean, you've seen the forward model of Monte Carlo with, thousands, millions of photons. It takes a long time to generate. As an inverse solver, you don't want to be changing optical property guesses and running it the forward sense every single time. That's somewhat insane. I mean, that's what we used to do. But with this scaled Monte Carlo or a white Monte Carlo, the strategy here is the separability of the absorption and scattering, where you can generate a kind of base Monte Carlo solution that is essentially scattering. And once you have that base pre-computed solution for any scattering guess, all you can do is just change the spatial scale. It's a semi-infinite solution. So you have, say, a base solution with a reduced scattering of 1 per millimeter. If you wanted to have a solution for something that was 2 per millimeter scattering, you just reduce the size. Essentially, you're increasing the density of that, and you just scale your detection accordingly for that. So you can kind of compress things for higher scattering. You can scale things larger for lower scattering. But, again, you have a single solution, and then you're just going back and forth. And that can kind of simulate now scattering at different values across different scales. And now if you're changing your different scales, you can then say, well, with Beer's law and absorption, we changed the scale, we're changing the path length of the photons from the simulation. We can then essentially paint this white Monte Carlo with any absorption we want after the fact. And so this becomes a quick way of just rescaling to calculate it without having to run a full Monte Carlo every single time. So that's the classic scale, but again, that's in the spatial domain. So how do we do it for spatial frequency domain? Because the standard Monte Carlo is in the spatial domain. It's exploiting the cylindrical symmetry just to get better statistics at farther distances. We know there's the transform between spatial domain and spatial frequency domain. So we can take these results, run the white Monte Carlo in the spatial domain, and then do a transform. And in cylindrical geometry, this is a Hankel transform instead of Cartesian geometry, where it would be the Fourier transform, and then go through and get the reflectance as a spatial frequency as opposed to reflectance as a distance. So that's usually the process for a standard Monte Carlo solution. So if you're reading about spatial frequency domain and they said, well, we used a Monte Carlo model, what they are typically doing is this, where they have that solution and go back and forth. Yep. Mm-hmm. Mm-hmm. Yeah. Yeah. Great. Yeah. Yeah. No, that's good to know because I knew there were at the time native spatial frequency domain Monte Carlos, but hadn't really come across this. This was the classical way that I think most people still use. So yeah, but shouldn't. Yeah. Okay. Yeah. Yeah. So even better. Good. Good. So I learned something every day. So yeah. So the key part though is with the transforms, the limitation is when it comes to kind of multi-layer stuff, the classical way, and with now the native spatial frequency domain, it'd be good to actually start to look at multi-layer aspects because doing the transform, going from spatial domain to spatial frequency, the volumetric information gets lost. You get the solution at the boundary. So that was always this kind of issue where trying to do depth resolved types of things, you would get depth resolved dependence in the reflectance, but you couldn't get access to the fluence anymore because of the transform. It eliminates that spatial information you had in the original Monte Carlo because it was in the wrong domain. But yeah, we'll get to that later. And of course, other things to just look at SFDI in general. There is this website. It's called opensfdi.org. This was a collaboration project initiated by Darren Robler's group in Boston University and has contributions from multiple different places. And, to try to collect and kind of give a general introduction and tutorial of how to get started with the spatial frequency domain techniques. So they have things about, building a very simple starter system from scratch. So what kind of components do you need to buy to build a very simple system for specific wavelengths, how to put it all together, how to do data acquisitions and how to interpret that data, and then tutorials on general processing in a very basic way. So at least you can get started and start to then build your own on an informed way. So, again, if people are curious, this is a resource. I don't know the last time it's been updated, but a lot of work has been put into it just to kind of get things started and kind of demystify SFDI, but also enable people just to do it in a more informed way rather than just relying on expectations. So, but yeah, so there are also deterministic solvers. So again, deterministic in quotes, but faster approaches. So, there are lookup table approaches. So the idea here is you can simulate results with Monte Carlo over a wide range of optical properties. If you pre-compute them for this specific spatial frequencies, you have two frequencies, you have two unknowns. You can have this direct kind of lookup table approach. The question really is which combination of spatial frequencies, because each combination, so if we have 0 spatial frequency and 0.125, 0 and 0.2, 0 and 0.3, you have a kind of different parameter space. And the higher the spatial frequencies, these meshes tend to collapse in space. So there's been a lot of debate on which one is optimal, which one is best. And again, no clear result. It really depends on what application you have, but also keep in mind that with a 2-frequency lookup table, you are evenly matched of the number of measurements versus the number of unknowns. So any noise in either measurement is going to directly impact the result you get. So again, even when you have a very collapsed parameter space, a small amount of noise in the reflectance here can have huge implications. So there's always a lot of noise sensitivity concerns when you do lookup tables. People like it because it's fast, but it's fast, but it doesn't mean that it's accurate. So those are always the trade-offs for that. And then there's also machine learning methods. So you have, say, in this case, 5 spatial frequencies, absorption and scattering as the output. You can have multiple layers. I've seen some papers. I am not a machine learning expert, but I hang out with people who are. In general, the comment is 2 layers should be more than enough for a Monte Carlo model or for a SFDI neural network. So, coming across a paper that has 37 layers, look at it with skepticism. But you have this, and we tried this out for low-cost instrumentation to say, can we process data on a Raspberry Pi? For SFDI, it's super computationally intensive. So we can simplify it to a simple low-level artificial neural network. How well does it work? So we had a master's student, and again, these were 5 spatial frequencies using a standard Monte Carlo. These were the same 5 spatial frequencies using the neural network that he had developed. And again, just the relative error bars, also comparing it to a standard 2-frequency lookup table, just the amount of errors, not perfect. We are looking at huge amount of noise. So yeah, this is 1%, 5%, 10% noise in reflectance. So if your image is that noisy in the reflectance, you really want to focus more on the instrument side of things. But at low noise cases, the performance was quite nice. So there are those different options, but you always want to check that out. And yeah. Yeah. Yeah, yeah. No, it was. It's the. Yeah, it's that whole mesh. So again, if you're basically saying what's the reflectance value at one frequency and the other. So if you have. So you can do interpolation within the mesh, but your raw measurement, any shifting in the reflectance value based on noise, there's no way to balance that. So these are with noise. Oh, sorry. So yeah, this is with noise. So I think, this was for the 5% noise case. And yeah, so I think this was about a 50% error. And in scattering, it was, around 50 to 60. So, yeah. So, yeah, it was pretty, yeah. But again, yeah, this was, very quick going through. And yeah, this was an international student. So, yeah, I'm like, all right, we got data. The whole thing is just the relative, for me, this is the gold standard. So, just to kind of see the relative change. But yeah, the absolute values, I don't recall exactly what they were. So yeah, okay. So yeah, so that's the basic data process, and we got 10 minutes left, so we get to go through all the fun stuff really fast. But yeah, so what do you do with it? what are the different implementations? So with spatial frequency domain imaging, there's a lot of flexibility. There's a lot of places to explore. And, when I was project scientist here, I was trying to look at the different parameter spaces and use cases for it. So I developed this little radar plot. I'm like, you can have things where, really high speed, large spatial range, large spatial resolution. So do you want to have a lot of spatial detail, a lot of temporal detail, cover a large area, cover a large spectral range, or a lot of spectral resolution? And based on the technology available in the components in either projector or sensor, there are certain compromises you always have to make. So you can have something that has really high spectral resolution, but it might be very slow. As a consequence, you can have things with different spectral ranges where you can cover large areas, but you tend to have limited spectral information, only a handful of wavelengths at that. And so there are the different compromises for these different systems. But yeah, so we had a line imaging spectrometer set up here for high spectral resolution. We have a high-speed camera here for high temporal resolution. And, this is the original, this is the intermediary, this is the product, first product that David produces at Modulin, the Reflect RS type system. But yeah, so we can just kind of go through, with space, these types of systems here, what you can do with it, with high speed, what you can do with it, and then with high spectral resolution, what you can do with it. So, again, these were, the greatest hits out of BLI back in the day. One of the main things looking at was burn wound severity, healing, and tissue viability. And again, David also showed similar things with looking at burn wound severity, where, just from clinical impression, looking at these, they all look pretty much the same. But if you can separate the absorption and scattering and start to look at that, you can actually see much greater differentiation that would correlate to the burn severity using SFDI. And again, looking at it visually, you can see areas that are not affected, areas that are. So you can even start to make spatial decisions and predict how that wound would respond. And again, I think David showed this as well, where you can look at tissue flaps. If there's an occlusion in some area, visually, from color, you can't really see that much of a difference. But, here, over large areas, not only can you see where there is some impact in the vasculature and the delivery of blood, but you can also try to spatially locate where that is, what main branch, so where that occlusion might be. So in terms of temporal resolution, again, you heard Yama's talk. You were all very excited by that. Yes. Yeah. So that was where they had lifted the two flaps, where they had primary arteries and veins going into it. So the one, it was left intact. The other one, they would put a balloon occlusion over either the artery or the vein, and then they could inflate that to a certain percentage. So that's where you've got this controlled blood flow reduction type of situation where there's a partial occlusion, so 25% occluded, so on and so forth. So that was the basic premise of that, that kind of experiment. Yep. So with temporal resolution, I mean, you've seen this before. So if you have a very high-speed SFDI system, that you can get this high temporal resolution, look at these kind of hemodynamic changes, acquisition times for SFDI, depending on what you're doing, it tends to be a very sequential measurement. So you have to have, if you have 5 spatial frequencies, 3 phases each, that's 15 sequences that you need to complete sequentially before you can get to the next acquisition. If you have multiple wavelengths, it could also take that time as well. So, you can, definitely have a low temporal resolution for a standard system. But here, They designed a very simple things, did a lot of different modifications to the basic premise of SFDI to make it high speed so you can actually map and look at these dynamic changes. But yeah, Yama already went through all that, so we can just show the pretty pictures. But how did they really go about doing that? And so now there are some interesting aspects. Yes. Yeah. So this was a scientific CMOS camera, and it wasn't just having a high-speed camera. You also had to have a high-speed method to project all the different patterns. So the SFDI system that they had here, I believe it was acquiring a full data set at 14 hertz. Yeah. So I'm not sure if they did any additional processing from that, but yeah, I mean, that was the kind of acquisition speed. I think it was 3 wavelengths, a few spatial frequencies, but they had a trick for that with a scientific CMOS camera. But yeah, that was basically the speed they were able to achieve with that. Yeah, yeah. That is my recollection at that point in time, what the acquisition speed was. They were quite proud of that. So how were they able to do that? So yeah, I mentioned they had a scientific CMOS. That's very fast. But if you don't get enough signal, it doesn't matter how fast your camera is if all it is noise. But for the projection side, a standard digital micromirror device to project a 8-bit sinusoidal pattern, it takes about 9.5 milliseconds to just generate the dynamic range of that. So now with every single pattern, every single phase, it takes a long time. But if you have just a 1-bit projector, it's much faster because you don't have to have that bit depth anymore. And so that's where this idea of, well, the square wave is just a superposition of a Fourier series. And to produce a square wave, you just need to have the mirrors on or off. You can then go really fast with the projector if you don't need to have all those shades of gray in there. And so, that's where the concept was, is that, you can just project square waves, and in tissue, it will get damped a bit. But based on the periodicity and the size of these square waves, you would have a fundamental frequency and then higher order frequencies. So you would have multiple spatial frequencies in a single pattern. So you can go really fast. The consequence, though, is every order is going to be weaker and weaker. So you get more and more challenged on the spatial frequencies. And the higher the spatial frequencies, the more sensitive you are to noise. So it is kind of a losing battle, but you can at least get 2 or 3 spatial frequencies out of this before you lose signal to noise. So you can do it really fast. Again, this was a publication from Kyle out of the group here, comparing, the kind of standard SFDI approach to the square wave approach. And you can kind of see, you start to get noise issues in these other parts, but you can have very fast. So this enables very fast sequences of patterns coupled with a very fast camera. Super expensive, but you can get it done. Other people have done analog masks to go very fast, so you don't have to deal with the digital issues and stuff. So you can have a standard mask, you can have that shifted left and right to do the different phases, or you can just do a single snapshot approach where you presume a spatial frequency and do fitting to get the amplitude out of that. There was a group out of Colorado that would actually put these masks on spinning discs. So you can have here 3 or 4 different spatial frequencies, 3 different phases each, and just spin it as fast as it can. As long as you're synchronized, you can then get very fast acquisitions, multiple frequencies, multiple phases at the same time. So there's these types of methods on there. You have spectral resolution. And again, so there's a spatial frequency domain spectroscopy. So rather than using SFDI as an imaging, this is more or less just saying, well, I'm going to image at a single pixel. and send that to a spectrometer and get high spectral information, no spatial information. And so here you can get spectral details a function of spatial frequency. And of course, here now, in terms of spectra, you can kind of see low spatial frequency, the sensitivity to absorption. And the higher and higher spatial frequency, you can see it starts to look very power law-like, like scattering. So you can kind of see that transition from absorption sensitivity to scattering sensitivity as a function of spatial frequency over a spectral domain. And again, separate absorption from scattering. And, one of the biggest critiques very early on, we were building the system to be both visible and near infrared. And everyone's like, well, that's useless because visible light only penetrates very superficially. Near infrared light goes very deeply. All your spectral information is coming from different parts of tissue. So it's never the same. So useless. And it was just like, well, but you have all these spectral measurements coming from different parts of the tissue at the same, like that is the most useful thing ever if you can go through and now begin to parse that out. And so that's where we started to do layered models where we can estimate the depth penetrance of every single wavelength, so know where each part comes from. Yeah. You had a question, or are you just sneezing? Or yeah. So again, we can kind of look through our measurement and actually go through and say, all right, these are the spectral responses we get at each wavelength, but this is the depth from which it comes from. So we know where all the data is coming from, or at least estimate that. And yeah, looking at things like skin pigmentation, we had this layered model approach where, this is just the example of the absorption spectra that we would have from a subject itself. But, knowing the scattering, knowing the penetration depth, we could try to estimate what the epidermal thickness is and how much melanin is within the epidermis by looking at the different regions here, fitting for the chromophores, knowing that they're sampling 2 different regions at different amounts. We could estimate what the melanin fraction was, how thick that top layer has to be, and then have a correction factor where we aren't subtracting the melanin spectra from the absorption spectra anymore. Since this is a depth-sensitive thing, there is this layer-specific correction factor. You can see that the hemoglobin has a little bit of an impact because of the variable penetration depth. So it's basically eliminating this partial volume effect created by melanin from the spectra, leaving a residual spectra here, which is the red one, which we then can fit for oxy and deoxyhemoglobin. But the interesting part is as we are going back layer by layer on this, it's almost like peeling an onion. You can also see there are certain parts that aren't matching up in this model. And if we look at those residuals, these actually respond to carotenoids, lipids. So again, typically in the subcutaneous layer, typically something that most people say in skin, we don't measure. But it's a very weak signal, but we can actually see that there in water. So we can start to now go back and get more and more detail, ask a lot more questions about that. So, what we did with that was to look at, what we can do with separating and quantifying melanin in depth. So we had comparative studies with multiphoton microscopy to say, does this diffuse optical technique, is it sensitive enough to be, on the same scale to detect layer thicknesses as microscopy can do? And, there is this correlation in that we can kind of do things like the depth estimation of melanin non-invasively and start to look at that. So I'm running a little bit over. I'll go very quickly, unless you just really need a break. So some of the newer things and new directions. So David also talked in his talk like where he thought things could be further explored with SFDI. And, again, it's so versatile. I think there's a lot of different corners that haven't been explored yet, and questions that haven't been asked. So another thing is multimodal approaches. We have our little schematic where I typically talk about absorption and scattering. Well, then what about fluorescence? So since it is kind of this tertiary effect, to solve for quantitative fluorescence, you need to know what is the absorption and scattering properties at the excitation wavelength what are the optical properties at the emission wavelength in order to go through and interpret, okay, how much light comes in to actually excite the fluorophore? And once excited, what is the probability that fluorescence photon is going to exit the tissue so you can detect it? So, what we did is, well, we can do that with SFDI, measure absorption and scattering at excitation and emission wavelength, and then be able to interpret fluorescence signals in a quantitative way by applying models to that. And so that's what we did here, where we had topical ALA, so protoporphyrin for photodynamic therapy, applied to the skin. After 7 hours, we could see there's a raw fluorescence signal here, but then also based on the optical properties and this mapping of excitation and emission wavelengths, have a correction factor. And so here we would actually have, now the contrast isn't just some relative scale of signal strength, but you would actually have quantitative values for drug concentration in skin. So you would actually have exactly how much protoporphyrin 9 was in the skin at these different locations. So, again, that was interesting, but, at the surface, especially for photodynamic therapy, you have a skin tumor that you want to have enough drug throughout the entire volume. So at the surface, it doesn't tell you if it goes deep enough or not. What we also found is that we can excite protoporphyrin at multiple wavelengths. So you can generate fluorescence from protoporphyrin 9 with blue light excitation, green and red. Blue, green, and red penetrate different depths. So you would get, a fluorescence map that was different from those 3 different wavelengths because they are looking at fluorescence derived from different volumes of tissue. So, from that same example, we were able to go through and just do a very crude reconstruction. And again, these are just cross sections at these 2 different places. Seem reasonable, seem to be, aligned with what literature proposes is that after 7 hours, typically it penetrates this depth. Plausible, but, how do we know it's right? So, again, really to move forward on this, we developed tissue simulating phantoms, where we can actually have molecular diffusion of protoporphyrin at different rates based on different water to gelatin ratios. So we can actually get different penetration rates. And since it's gelatin, we can also just slice it open, look cross-sectionally, and actually see what the answer is, what the correct distribution is. And from this, we were doing just from these 3 wavelengths, the same tomographic reconstruction. We're able to reconstruct, from the intact phantom, very encouraging resolve things from just this SFDI approach. So, it's a sanity check to do this depth resolve, utilizing the same kind of spectral penetration depth that we did with our melanin epidermal layer type of approach we can apply here. So the only, spectral is not the only depth sensitive thing. Spatial frequency is a similar thing. And I think David, brought this up as well, where if you vary the spatial frequency and look for fluorescence generation, the higher the spatial frequency, you start to lose signal from deeper. You only see things from very high up that you can go through and start to differentiate. It's not that it's a weak fluorescent signal, it's a deep fluorescent signal. You can utilize this. And so there's this additional depth sensitive lever based on spatial frequency. We've done that as well to do depth resolved scattering based on spatial frequency. So, we know that different spatial frequencies have different sensitivities to absorption and scattering. And so typically multiple spatial frequencies, you can go through and process that, get your absorption and scattering. But then we ask the question, is like, well, what if we continue to do that? Especially since, if we're not interested in absorption at higher spatial frequencies, contrast for scattering persists. So what if we did it again and again? Every single time we go to higher and higher spatial frequencies, we're looking at smaller and smaller volumes. Changes in scattering would represent changes that are from the superficial versus the deep, that we could do similar type of reconstruction. And that's what, we are doing here is we had 2 different scattering phantoms and the top layer would have different thicknesses. So as a function of spatial frequency, we should have our average data shift toward the more superficial. And that's what we were seeing, is that, you would see this transition between contributions from bottom layer versus top layer, and that transition would represent what the thickness was in between. And that came out to really help looking at new cell growth. So in wound healing, where you have new cell growth having different cellular morphology than the underlying tissue, just from the scattering contrast using that type of approach, we could actually look at how well and how effective different cell-based therapeutics were working on wounds. And this was an ex vivo example of 3 different preparations that a colleague of mine had with a control. We just looked at scattering contrast and set a scale up, and could see that there were different amounts of new cell growth based on scattering. And then he looked at histology, and there was a direct correlation to that thickness. But the key point here is, with histology, it's a single slide. It's looking over a very small area. These wounds were 3 centimeters. And yet we could go through and get this kind of 100 to 50 micron layer thickness contrast over large areas, non-invasively from this technique. So that was really kind of exciting to be able to look at that. We can go into subdiffusive scattering now, take it even further into higher extremes. People have shown that, all right, if you start going beyond 0.5 per millimeter spatial frequencies and go higher and higher and higher, you're looking at smaller and smaller volumes. You're looking at less and less scattering events. This is now in the subdiffusive regime where you still have angular components. It's not isotropic anymore. So it's much more complicated, but what they were showing is that it's also interesting because you start to see more features that you wouldn't normally see from scattering itself. Just nobody knows how to really model it. Nobody knows how to explain it. It's just, empirically, there's some new information there, but what do we do with it? So, the big problem here is with a reflectance geometry, you're always shining light. There's always going to be a diffuse component and a subdiffuse component in everything you do. And so it's really hard to characterize one thing that's very weak when you have a large background system that you're trying to eliminate. You can subtract most of it, but the noise always goes through. So it's really hard to interpret that data. So we have this idea is to say, well, in order to eliminate that, if we go into a transmission geometry, we can limit the thickness. That will limit the number of scattering events. We can go to higher spatial frequencies. But, since we aren't in a reflectance geometry, we don't have to deal with that diffuse background anymore. So we can go through and separate that. And, again, we've done proof of concept tests, even say in terms of tissue slices and looking at variation in morphology. This is a phantom where we had 2 different scattering particles of slightly different sizes. So we made one with one size, cut a hole in the middle, filled that with the other one, and effectively it all looks white. Yet just based on the B parameter of scattering, we can see the contrast based on this transmission type of approach. So it's kind of encouraging in terms of focusing only on scattering and what it can do, that you can start to ask these questions. And of course, this is a $150 projector, a $50 camera to go through all that. And you can also rotate the patterns if you have organized things like collagen fibers that have a directionality, and actually look at that kind of scattering differences if you are aligned with fibers versus perpendicular to fibers. And you can read that later. So sorry for the overrun. I get excited by this, but I think there were a lot of good questions along the way. So, it was good to have that. Thank you.